morning. This is the second lecture in the series on inverse function theorem and its applications. Okay, so you may recall yesterday we motivated and formulated the inverse function theorem in a precise way. We also proved, we saw the proof breaks into three steps. The first step was one-one nature, local one-one nature of the function. Okay, I hope all of you remember the thing because I don't want to repeat. Okay, then it will be taking a lot of time, but anyway, so let us now today what we are planning to do is we are going to show the openness of the map. So let me recall what our assumption. Our assumption was U is an open subset of Rn and F from U to Rn is C1, and we assume the A is in U and DFA is non-singular, right? Then what we found out yesterday, what we proved was there is an R positive so that F is 1,1 on BAR. Not only that, this R was in such that dfx for each x in is non-singular for each x in BAR. This also we saw, right, which chose R in such a way that for each x in BAR dfx is non-singular, and then we proved F is 1,1 on BAR. And what are the crux of the matter? The crux of the matter was we proved it with extra simplifying assumption. Assume that this one. Remember, the proof works for anything. We also showed how it is done, and the key idea was this inequality, the so-called mean inequality, fx1 minus fx2 minus x1 minus x2. This is actually dfp acting on x1 minus x2, but that's less than or equal to dfz minus identity into norm of x1 minus x2, where this is LEB of z varying over the line segment x1 x2. Okay, this was a key inequality which allowed us to do that. Okay, now what we want to prove is one-oneness. So what do I want to prove? I want to prove f of BAR is openness. Sorry, did I say one-oneness? Okay, this is what we want to prove. This is step 2. We want to prove BAR is 1,1. Okay, right. So let us go through the proof. Let's try to understand. What I am actually going to show is f of A is an interior point and of f of BAR. Okay, this is all we want to prove. All right, so it's enough if I assume that f is C1, okay, and dfa is non-singular, and I chose an R so that it satisfies both these conditions. Then I want to say fa is an interior point. Okay, let us prove this, then we will see how we can extend it much better. Okay, so we want to prove this is non-singular. So let us try to understand what this means. So I have A and I have BAR. Okay, okay, maybe this BAR, I don't think this is not a good thing, but anyway, you understand. So I tried to draw nicely, but it didn't come out. So this my A I can change now. Yeah, this is not my A is something else. This is my A, right? This is BAR, and therefore let us look at let us look at S equal to set of all x in Rn so that norm of x minus a equal to r. That is this boundary. I usually denote it by SAR, sphere of radius r centered at a. This is only the surface, not the ball. You understand that? Okay. Now what do you know about this? Yes, S is closed and bounded, therefore it's compact by Henry-Borel theorem. Right? Let's look at image of f, image of s under f. So this may be my f of s. You understand that? Right? My fa is going to be somewhere here. So what do I want? I want to say there exists an open ball centered at this, which is completely contained in f of a. So this is my f of bar. Okay, this is, and I want to say there exists an open ball containing f of a, which is contained in f of bar. Therefore a becomes an interior point. Yeah, okay. Now let's do that. Okay. Right, now what is the problem? See, let us look at, so we can, with a loss of generality, I can assume my R is chosen such that even the closed ball bar is contained in U. Right, if necessary, string R. Okay, alright. And again we are assuming on the open ball bar it is okay, dfx is non-singular, etc. for each x in bar. Okay, is that all right? Okay. Now what do I want to do? Now if I look at, start with a y here. Okay, so I do not know what delta I have to choose. Okay, so I want to say there is a delta positive, so that b fa delta is completely contained in f of bar. Okay, I want to choose this. Therefore if you give me a y in here, right, I want to say there exists x where in bar, so that y equal to fx. You understand that? That means every point in of the ball b fa delta is completely contained in f of bar. Is that clear to you? Yeah, okay. So if such a thing happens, what will happen to y minus fx? Y minus fx will be 0 if I can find such an x. Right? So the basic idea, I like this proof because it uses a lot of calculus notions. Okay, there is another proof we will see later if time permits. Okay, let's look at this. So let's look at bar. This is a closed and this is again compact. Right? Now let's look at the function for x here. Okay, x here, we will map it to fx minus y. What is y? I still do not know what is the delta, but I want to find such a delta. Right? Let us just keep it. Okay, we do not know whether it is okay. Right? If I want to say any y is in the image of the ball bar under f, then this should be 0. Therefore you can see if such a thing is true, this must be 0. The minimum should be attained here. You understand? The minimum should be 0 and it should be attained. When I say minimum, it's of course it means attained. Do you follow that? Okay. So the trick is, since it's compact, we know there exists a minimum, right? This has a minimum, say at some x in bar. Okay, because this is a real valued continuous function on the compact set, therefore it attains a minimum. Why it's a real continuous function? Because f is differential, therefore f is continuous, therefore fx minus y, x beyond fx minus y is continuous, now followed by norm. Therefore this is a continuous function. Yeah, all right. So what we want to claim is fx equal to y. This is what we want to claim now. Do you understand this? Are you able to follow my thinking? Okay, right. Okay, so I still do not know what delta I ought to choose properly. Okay, let us do that. Okay, now the problem you can say is this minimum may be attained, that's okay, but the minimum may be attained on the boundary of the ball, because only the closed and bounded set, therefore my x may actually be somewhere here. That is the closest. You understand that? So I hope to say that x cannot occur on the boundary, that is on, it cannot be on the sphere. It should be, sorry, not here, I'm sorry, this is not my x is here. Okay, this is my bar, therefore my x may be here, therefore my fx may be somewhere here. You understand that? So I have to say x cannot be on the boundary of the ball bar. Okay, so I have to make sure it does not happen. Okay, let us see how to do that. Okay, fx, okay, right? Yeah, so let us try to find out. Yeah, see, one way of doing would be look at this set S, which is compact, and f is continuous, therefore fs is compact. You understand that? Right. Okay, next, also can fa belong to f of s? Notice that a is in the center, but a may take, f of a may actually be here also. F of a is here, but it may also be here. Yeah, so I want to say this cannot happen. So what is our assumption? So we have to make sure you are choosing an R positive, right? If you necessary, you reduce your R to R less than R, R1 less than R. Okay, therefore on BAR1 is contained in BAR, and f is 1 1 on this, therefore f is 1 1 on this also. Do you understand that? Therefore f of a, okay, so what do I have? So our assumption is assume f is 1 1 on the closed and bounded ball order. In that case, okay, choose R such that, okay, dfx is non-singular for every x in BAR, and closed BAR is contained in U. Okay, then we have BAR is 1 1. We had already shown that. Okay, right. So let f is 1 1 on this. This is our assumption. Therefore, yeah, f of a cannot be equal to f of x if x is in U, on the boundary. You follow that? Now therefore let's look at the function x going to norm of fx minus fa. Okay, this is from the boundary to R, right? And this is always positive because fx is not equal to fa. Now s is compact, therefore it attains a minimum, right? Therefore this attains a minimum, right? Say the minimum is 2 delta, which is positive. Okay, so let us look at the picture. What does it mean? This is a f of a. I am looking at all possible distances. Okay, the minimum distance is 2 delta. Okay, for the picture it looks like this is the minimum distance, 2 delta. So you choose only half the delta. So what we are going to do is we are going to look at BFA delta. So let y belong to this. Then I want to claim there exists an x in the open ball BAR such that fx equal to y. This is what we want to claim. Okay, please note that I am thinking aloud, so therefore it may be going back and forth. Don't get confused, just try to think along with me, then you can always read a book, then you will see things will become very crystal clear, because you know what is happening. You are not simply verifying the proof line by line. Okay, this is what we want to prove. Okay, now what was our assumption? Now what we did was, well, let us look at the closed bounded ball to R and look at the function. This is fx minus y, where y is in B fa delta. right? So we know it attains a minimum, say at x in BAR, right? What do I want to say? I want to say this minimum point x cannot be in S. Therefore x must be in the open ball BAR. Right? Why do I want to prove? If that means x will be the minimum for this function is attained in the interior, right? Therefore I can apply the post derivative test to show the something to do with the derivative 0. Intuitively that's what I have ideas. Okay, so I want to prove x is not equal to S. Suppose x is in S, okay, assume the contrary. We have to arrive at a contradiction. Okay, now what are the facts? I know x is in S, therefore what do I know about fx minus fa? So what is our assumption? Let's look at that. For all x in the sphere, norm of fx minus fa is minimum is 2 delta, therefore this is greater than or equal to 2 delta. Yeah, but I want to arrive at a contradiction, so I have to make use of that fact. So let us do that. Therefore let us look at fx, okay, minus y, right, plus fa minus, so what is that I should look at? So I want to arrive at a contradiction, therefore fx minus fa should be fx, I know fx minus y is minimized, okay, therefore I should have a y here, so y, yeah, this is okay, this is plus y minus fa plus y is equal to this. You understand that? Fx minus fa equal to fx minus y minus fa plus y. You understand that? Yeah. Now this is equal to norm of f less than or equal to fx minus y, okay, plus fa minus y. Do you understand this? I'm just using triangle and equality. Therefore norm of fx minus y should be greater than or equal to 2 delta minus norm of fa minus y. Yeah, but what do I know about a? A belong to f of a delta, therefore this will be norm of fa minus delta, sorry, minus y will be greater than less than delta, therefore negative will be greater than or equal to minus delta, therefore this is greater than or equal to 2 delta minus delta equal to delta. You understand that? So if x belongs to S, then I have said norm of fx minus y should be greater than or equal to delta. Please pause, review, proceed. But let's look at this function. Where is this function? This function x is from norm fx minus y. This is on the closed ball BAR, right? Therefore what is f? What is the value of the function a? That is fa minus y. You understand that? This is call this function phi or something, okay, or something, okay, alpha. Then alpha at a equal to norm of fa minus y. But what do I know? Y belongs to the open ball, okay, it is less than r, okay, sorry, less than delta. Go back, okay, it's less than delta. Yeah, okay. Therefore the function, we know the function has a minimum, and the minimum should be, okay, the one of the values of this function is already less than delta, therefore minimum of this function alpha should also be less than delta. Do you understand that? Yes, but what did I see? At x it attains the minimum, and the value of the function alpha x is fx minus y. We know it's already greater than or equal to delta. That's what we proved. So what does this contradiction shows? So this implies, okay, our assumption that y belong to S is wrong, cannot happen. That means x belong to S cannot happen. Therefore, x belong to BAR. Okay. Please pause, review, proceed. So what you have shown is the function alpha, which is from closed interval closed ball BAR to R, given by x going to distance between fx and y, that is norm of fx minus y, attains a minimum at x, which is in the open ball BR. This all we have proved so far, right? Okay. Now we know that if I have a differential function, if the extremum is attained at an interior point, then the derivative has to be 0. That we have seen in our previous lectures on differential calculus, right? Then we want to compute that, right? So what do you want to do? Let us look at. Now remember, this is a norm. It will be easier whenever you deal with norm. Okay, remember this. Okay, it will be easier to deal with norm squared, that is inner product. Therefore, let us look at alpha squared. Alpha squared x equal to norm of fx minus y whole squared, which is inner product fx minus y, fx minus y. Yeah. So this function alpha will be attaining its minimum at x or x naught. If you want, call it x naught the minimum where it is attained minimum. Okay. Okay. Therefore, alpha squared attains minimum at x naught, which is in the interior BAR, in the open ball BAR, right? Therefore, the derivative must be 0. So I want to compute the derivative of this function. Yeah. Right. Now you see why I like this proof. We used already a lot of idea, right? There is a geometry, there is analysis, Henry-Borel theorem, and Bolzano's theorem, which says on the compact set the continuous function attains its minimum maximum. See, that's why I like this proof. A lot of good analysis is involved. Okay. Now we want to use derivative also. Okay. Now we want to compute the derivative. Again, you see that if you watch my lectures on calculus on several variables, you will see I always try to reduce the computation of derivative by writing the function as a composite of functions and invoke chain rule, right? This function is a composite of two functions. What are they? X going to fx minus y, and that going to the dot product. So this is going to be, okay, x, this is an Rn, this is going to be an Rn, and from Rn to R I have a map. What is the map? Z going to z dot z. Okay, you understand? And call this map as y, this map as xi, right? Therefore my alpha squared is nothing other than xi composite phi. Okay, maybe let me call it beta so that I don't know to write alpha squared. Okay, the composite function beta, where what is beta x? That is norm fx minus y whole squared, is xi composite f. Therefore d of beta, okay, at the point x naught must be 0, right? Now let's compute that. So let us compute this. So this is d of xi at which point? Phi of x, and followed by, let us say, acting on some vector h if you want, d of phi at x acting on h. Yeah, is it okay? Right. Now let's compute this. From our earlier lectures, we had seen it many times. Oh, okay, somehow it is going on back and forth. Where is it? Okay, right. So what is d xi? Xi is inner product. Okay, remember xi is z going to z dot z, we know what is d psi z acting on h. D psi z acting on h is 2z dot h. I hope all of you remember that. Yeah, okay. And next what we want to do is d phi. Okay, so d phi, this is d psi, right? Yeah, right. And what is d phi of x? That is going to be, remember phi of x is f of x minus y, therefore this is nothing other than df of x acting on h, you know that, right? Therefore d beta of x acting on h equal to d psi of phi x, that is phi x is fx minus y, and d phi x dot x, that is derivative of fx acting on h. Do you follow that? And this is your z, therefore d psi z acting on any vector is going to be 2z, that is going to be 2 times fx minus y 2z times whatever h is, this dfx h. I really love this proof because, okay, if you are not sure of how to compute the derivative, chain rule, etc., okay, this will test you, it will challenge you so that you will be forced to learn it better. Please go through this proof again. If you are confused, go back to chain rule, learn it again and come back, right? Therefore at x naught, this must be 0. D beta of x naught acting on h must be 0. That means, okay, fx minus y and dfx naught acting on h must be 0 for which h? For all h in Rn, right? Now what do I know about dfx naught? Remember, x naught lies in bar, and what was our assumption? For all x here, the derivative dfx is non-singular, therefore dfx naught is non-singular. Therefore if you give me any vector in V in Rn, okay, there is an h, that's that V equal to dfx naught h, because this is non-singular, right? This is invertible, therefore I can solve for this. That means fx minus y inner product with V is 0 for every V in Rn. In particular, when I take V equal to fx minus y, what do I get? Norm squared of fx minus y is 0. In other words, fx equal to y. Fx minus y is 0 or fx equal to y. Have you understood the proof? Please go through the proof. Do not feel intimidated, okay? Because many times some people do not pay attention how to compute the derivatives and how chain rule is one of the most useful tricks to learn. Of course, one can also directly compute by the first principles, as I have been doing in my lectures, but it will be a wonderful occasion for you to test your knowledge. Okay, please go through it. So what I have shown now, I have shown that for every y in B fa delta, okay, there is an x in bar, said that y equal to fx. That means fa delta is contained in f of bar. That is, fa is an interior point. Do you understand this? This implies fa is an interior point of the ball. Okay, pause, review, proceed. So as an immediate corollary, suppose you use an open set in Rn and f from U to Rn is C1. Assume that, okay, f is 1 1 on U and dfx is non-singular on U for all x in U if you want. Okay, then f of U is open. This is what you want to prove. Is that statement clear? F is 1 1 and derivative of f is non-singular, then f of U is open. Why does it follow? Because you start with any a. In U, I have to prove fa is an interior point, f of U, right? Then what can I do? Therefore dfa is non-singular, so as usual I can assume after composing with the derivative inverse, I can compose. Okay, I can okay, we had already proved that. Okay, so what do I know? There is an R positive so that, and BAR, okay, or the closed BAR is contained in U, and f is of course 1 1 on this, and for all x in BAR we have derivative of x is non-singular. You understand? Therefore by the last thing I know fa is an interior point of f of BAR, but f of BAR is contained in f of U, right? Therefore for each a, fa is an interior point. That means, okay, under the stated assumptions, okay, f is an open mapping. If you know, if you studied topology, you know a map between two topology spaces is said to be open if it maps open sets to open sets. So in the differential category, what we are having is, if f is a C1 map which is 1 1 on U, and the derivative is non-singular at all the points of the domain, then f is an open map. Okay, this is what we have proved. Please pause, review and proceed. Hi, let us continue. So the proof which I just now gave, as I said, I am fond of that proof because it uses a lot of analysis and intuition, geometry, calculus, topology, various things. But then there is another proof which is very standard and which is also very popular because of the most famous textbook on analysis. Okay, a lot of students only learn from that and they find the proof to be very terse, so they get confused. So let us indicate that proof also. That proof uses contraction mapping principle. So let us quickly recall and do that. So what does contraction mapping principle say? It says that Banach contraction principle or some such thing, or fixed point theorem. Okay, XD is a complete metric space. Okay, and if f from x to x is a contraction, that means there exists a alpha between 0 and 1 such that distance between fx1 fx2 is less than or equal to alpha times distance between x1 and x2. That means f has a unique fixed point. I hope I did it correctly. So we want to make use of that. The way we to do that is, so what we want to prove, let us recall. Okay, we have BAR, okay, and it may be contained in something in U, and what is our assumption? For all x in BAR, dfx is 1 1, and we also proved that f is 1 1 on BAR. Okay, all these things we have done. Okay, and what we want to show is that f of a is an interior point of f of BAR. This is what we want to prove, right? So that means we want to say there is a delta positive so that, okay, B f a delta is contained in f of BAR. That means you give me any y in B f a delta, then there is a x in BAR such that y equal to fx. This is all we want to prove. And as you might have learned when you learn contraction mapping principle, it is to solve equations of this kind, that is y equal to fx. So you try to get it as a fixed point. Okay, it must be a fixed point, but then it must of a function, a contraction from a complete metric space to complete metric space. Okay, now what do I want? I want this x to be in the ball BAR, open ball BAR. All right, you understand that my x must be got as a fixed point, right? But I actually want to solve the equation y minus fx. So what should be the thing I should consider? I should consider f plus y minus fx. Consider this phi of x equal to this. Okay, then phi x equal to x if only y minus fx is 0. Do you understand that? Yeah, right. So this must be in BR. But remember, I want to find such an A in the open ball, but then for contraction mapping principle I need a complete metric space. Therefore what do? I take the closed ball BAR. This is a closed subset of Rn. Rn is complete, therefore this is also complete metric space, right? Therefore, so for x in BAR I define phi x to be like this, but then I have to make sure two things. One, I have to make sure phi maps the closed ball BAR to the closed ball BAR, and then phi is a contraction. Okay, these two things I have to check, right? But what we are actually but if I check, then what will I know? There is an x in where? In the closed ball BAR, such that phi of x equal to x. But what did I want? I wanted x to be in the open ball. Okay, so what we are actually going to prove is we are going to prove one in a slightly stronger way. We are going to show phi maps the closed ball BAR into the open ball BAR. Okay, under suitable assumption. Okay, now remember what are our assumptions about R? Our R was like this: dfx minus identity is less than half. We always assume dfa is identity for simplicity's sake. Okay, so we have to use it. So let us see. So what is that I have to check? Take x in BAR, and then I have to say phi x belong to BAR, therefore I have to estimate this. But what is this? This is, what is x? X minus fx, or I don't remember, plus f plus y minus fx. Okay, plus y minus fx minus a. Yeah, now what do I want? This y I do not know. Y belongs to some b that is distant between, that is norm of y minus fa is less than delta. I do not know what is delta. Okay, I have to fix such a delta. Please remember that. Okay, delta is not yet given to me. I have to do that. So I only know when I want to estimate. What do I know? This look at x fx. Therefore I know also how to look at fa also, right? That is y minus fa also I know. Therefore I have to rewrite this as x minus a minus fx minus fa plus fa minus y. You understand this? Because I know how to estimate y minus fa, so I have to introduce that. Okay, then why do I have to do that? This is maybe this is plus y, therefore let us say this is minus, this is plus y, this is plus fa. Are you following me? Y minus fx minus a is there, and I want this plus y, therefore it should be minus fa. Alright, therefore I have to add plus fa, right? But this is less than or equal to norm of fx minus fa minus of x minus a plus norm of y minus fa. You understand that? By triangular inequality. But remember, where do x belong to? X and y belong to the closed ball BAR, on which we are assuming this is less than half, right? Therefore this is less than half times norm of x minus a, but then this less than half. This is r, right? Less than or equal to r. This one. Therefore this first term is less than or equal to r by 2, less than or equal to. But then what do I know about y minus fa? norm of y minus fa is less than delta, but I want the whole thing to be less than r. So what should be my choice of delta? Choose delta to be r by 2. Therefore norm of y minus a will be strictly less than r by 2. Therefore this inequality is strict. Have you understood? Okay, pause, review, proceed. So what you have shown is my phi maps BAR to the open ball BAR. In particular, it maps into BAR. Yeah. So what is my y now? Therefore my y is going to lie only in BFA R by 2. That is the way I am going to do. So what my plan is to show? My plan is to show BFA R by 2 is contained in this ball. Alright, okay. Now we have proved phi maps the closed ball BR into the open ball BR. That's okay. Next I have to check phi is a contraction. That means what? I have to estimate phi x1 minus phi x2. Okay. So what is phi x1 minus phi x2? That is x1. What is my phi? I always don't remember whether I put a plus or minus. It does not matter, but it's good to know. Y minus fx1. Okay, minus of x2 plus y minus fx2. Yeah, but this is nothing other than x1 minus x2 plus equal to fx1 minus fx2 minus of x1 minus x2. I am taking negative of everything, right? But where are x1 x2? They are in the ball, closed ball BAR. And what do I know on that? That we had already checked our inequality. That's less than or equal to, yes, half of norm of x1 minus x2. Okay, this is the first inequality we established. Do you remember that? Therefore phi is a contraction. Okay, therefore phi is a contraction from here to here. Therefore there is a unique x in where? In the closed ball BAR, such that phi of x equal to x. But remember, phi x always belongs to the open ball, but phi x always in the open ball BAR. Therefore what do I conclude? Therefore x also in the open ball BAR. You understood that? Right? Therefore there is an x in BAR, of course a unique x, so that what happens? Phi x equal to x. That is same as saying fx equal to y. Right? Therefore we have proved. Therefore what have we shown that? We have shown that the open ball BFA R by 2 is contained in f of BAR. That means FA is an interior point of this ball, this image. Is that clear? So this completes the proof. So you notice that this proof is very slick and very nice. The advantage of this proof is better because it's somewhat much neater, simpler. And the most important thing is, let us compare the earlier proof of mine and this one. The earlier proof of mine actually I learned from Apostle. Okay, but that proof uses, as I said, lots of mathematics. Whatever you have learned in analysis and R and so far, we have used all of them. Okay, that way it's very nice proof. But remember, we used finite dimensionality. Why? Because we said a closed and bounded subset of Rn is compact. Like S is compact, the closed ball BR is compact. All those things we used in the earlier proof. Right? Therefore, we needed the domain of the function f to be a finite dimensional space. But this proof, if you happen to go higher studies, you will see this proof works in unique complete non-linear space, or otherwise known as Banach space. You can talk about differentiality of mapping from a complete non-linear space to another. Okay, talk about derivative, various things, right? Then you can also talk about the inverse function theorem. This proof works even in infinite dimensional space. That is the advantage of this proof. Okay, so that is why I decided to give this proof also. Okay, and one can also avoid contraction mapping directly proving it. Okay, you can see it in my book on differential geometry and Lie grooves, or you can also see in my forthcoming book with Santana. That proof will be given, but instead it will be a lot of people who like this proof because contraction mapping comes in a jiffy. Okay, so I hope all of you like this. Okay, in the next lecture we will prove that. Therefore, what I have shown now, I have shown that the first two steps are over now. F is 1 F is open, or whatever it may, under stated assumptions we have shown that. Next I have to prove F inverse is differentiable. That we have to prove. In the next lecture we will do that. Okay, till then, stay safe, take care.